Okay, so this is the first time I've tried to do a screen capture view, but we'll see how that works. So a lot of you have been saying that the curve fitting parts of Matlab have been giving you some issues, so I'm going to try to clear some of that up. So there's basically three types of curve fitting that you are definitely required to know, and that'll definitely show up on the third exam. So those three types are, excuse me because I don't have a tablet, so this might take a while. Polyfit, basis functions, and nlinfit. Okay, make sure I spell this right. Okay, so it's important to actually think of these as being somewhat related to each other because they're all trying to do the same thing, and that's why Sophocles will often ask you to try to do the same problem over again using a different method. So let's go over polyfit first. So polyfit typically works if you're given a polynomial. Well, you pretty much need a polynomial. So say we had a degree 2 polynomial. Well, then you're looking at something in the form of ax squared plus bx plus c equals some y. So the general form of the polyfit you're going to be looking for will take the arguments x, which is a set of values you should have already, y, another set of values you already have, and the highest degree of the polynomial. So in this case, that's going to be 2. What this will return is a vector containing a, b, and c. Okay? So what does the basis functions do? Okay, well this is confused probably a few of you because the idea really comes from something called linear algebra, which you could take as a technical elective later, but you probably won't be going into it. So say I have some sort of system that can be written like this. I'll keep it concise and make it a 2 equation system. Okay, so some of you might remember from high school that this can be written in the form of a x equals y, where a is something called the coefficient matrix, and x and y are vectors. So what that looks like is you compose a of just these coefficients here, 3, 2, 6, and 5. Your vector, well, here let me change this. This will confuse some of you. Here your unknown vector is x and y because you're essentially taking dot products with this. And over here is the values you have. So 5 and 11. And you can do tons of cool operations with this. The takeaway lesson is that if you wanted to solve this equation, what you do is you multiply both sides by something called the inverse. So if you took A inverse and put that on the left of both of these equations, what you get is, well, these canceling out, and you've solved for the unknowns. Now in Matlab, A inverse times C is pretty much done by A left division C. Okay, well there's a few comments I'd like to make for those of you who actually care about linear algebra. What we're dealing with basis functions is something a little bit different. So you're instead solving a system that looks like this. And what you have is, say, these two equations, which you know must be true, and some x values you know that make them true. So let's say the values that make this true are x equals 1 for the first one and x equals 2 for the second one. So your A, or your coefficient matrix this time, are going to be your knowns. So we sub in 1 here, and we get 1 squared here. We sub in 2 here, and we get 2 squared here. And our unknowns this time are A and B. And again, our constants are this. So if you wanted to solve for A and B, what you do is take this coefficient matrix A and left divide it by what you find over here. And that would get you this. Maybe too many arrows. P, which are the coefficients. So this isn't exactly what's going on with the linear algebra, because those of you who've taken it know that you need a square matrix to have an inverse, but it is essentially a good simplification of what's going on. So what's the difference between polyfit and the basis functions? Well, in polyfit we needed polynomials, so we needed these exponents here to be integers, and integers that decrease with a degree. So if we had a third degree, we'd have a third degree term, a second degree term, a first degree term, and a 0th degree term out here as the constant. For basis functions, you're not bound to that restriction. So what you could have is something like, instead of x squared here, you could have something like 1 over x and 1 over x here. What that would change is that your second column over here would become 1 over 1 and 1 over 1 over 2. Yeah, 1 over 1 and 1 over 2. Okay. So nlinfit is pretty much like the end-all be-all for regression fitting, because it's like, alright, well, this didn't work and this didn't work, what else do we have left? Well, the N stands for nonlinear fit, so you don't even need to be able to express this function explicitly. So this one will make a lot more sense when we look at the actual code, but basically you need a function of C, which will be the coefficients that you're looking for, and the x values. And I'll try to explain this one more later. But let's jump straight into doing actual problems, because that'll probably make things a lot more obvious. Okay, so the first problem here is we have some viscosity of air, some great flavor text that Sophocles loves to throw at you, and we have several equations. Okay, so he gives us this, this, and this. And the first part of the equation wants us to polyfit this function. So we're also given initial values here, initial values in temperature, in degrees Celsius, which we'll probably have to convert to Kelvin. And we're given viscosities. Okay, so these are probably going to be our dependent variable, and this is going to be our independent variable. More on that later. Okay, and it wants us to polyfit. So when you're polyfitting, you need to look for the equation here that is a polynomial. So this fails because it does not have integers in the powers. This fails because it is not written explicitly in terms of temperature. This works just fine because you have a first degree here and a 0th degree here. So that's what we're going to use. Okay. So before you even start coding, there's a lot of analysis you can do, because most of this is actually math. So here we have t to the 3/2 over v, and big T and small v are both going to be vectors. Okay, so even here we can set up a polyfit. So the highest degree we have here is 1, and that's going to be from from this t over here. Okay, and what is our dependent variable? What is the polynomial written in terms of? Well, it's written in terms of t. Okay, so what is the y? Okay, and this is what confuses a lot of people because most people will just put v. Don't do that. Your y is going to be this entire expression over here. Y, well, let's see if I can get some colors here. This a is m, this is your x, this is your b, and this entire expression over here is y. So we follow exactly the form that it's put in. You're going to have t to the 3 halves over v, and 1 here. So let's actually see what the code for that looks like. And now for the very fun part of watching me enter in these numbers. 405, okay. Should we go for that? This is gonna suck. Hopefully I'll get them all correct on the first go. We won't get any errors. 3.32, 3.64. Okay. So the polyfit, I already told you, is going to be t to the 3 halves. We're going to have to be careful about the dot operators and stuff like that, but I'm just going to worry about that once we get error messages. And I'm sure we will. Alright, yeah, great. Because I call it TCI. So again, we had to convert this to Kelvin, so I'm just going to use a conversion factor there. And matrix must be square. Okay, that's the result of not having a dot here. So, okay, this is what you get. So this would be A, and this would be B. Okay? So hopefully that made sense. So the next part of the question is, okay, repeat this, but using the basis functions. So usually Sophocles will tell you exactly what basis functions you have to use, but we're looking at this over here. Okay, so again, we could go through that analysis in Paint, but I'm going to shortcut a bit. So remember, for the basis functions, you're going to need two things. You need a coefficient matrix A, and you're going to need some sort of known, which is going to be y. So the coefficient matrix is something he already tells you with this as the basis. And again, your t's are already known. These are your initial values of t's. So we're just going to put that in. We have t to the negative 0.5 and t to the negative 1.5. Cool. Let me just make sure that that comes out right. Yeah, so you should always check it. And here we are going to want 2 columns. So hopefully what we got is 2 columns. That could be the result of not transposing this. Oh, great. So then I have to transpose this. And finally this. And untranspose that. Okay, sorry if that was confusing. But I knew I needed a matrix that looked like this with 2 columns. Okay, likewise with the y, you just read that off from over here. So your y is not v, it is 1 over v. And that's also a column. So simply all you need to do is take that coefficient matrix and left divide it by whatever your y values are. And this is what you'll get for A and B. Okay? Nothing too complicated, I hope. Make sure that these match. Okay, that's a little weird. Those are usually a bit closer than that, and that's because, yeah, okay, so remember, order of operations are pretty important, so hopefully that won't make you too upset. Okay, so the last thing it wanted us to do is nlinfit, or as LSQ curve fit, but like no one likes that, so we're just going to do an nlinfit. So the nice part about nlinfit is that he'll pretty much always help you out and give you this setup. So this is pretty much exactly all you need to be able to do is write that anonymous function. So literally just copy down what he has there. Again, be careful, more careful than I am about getting the dots right. And the nlinfit is always going to follow this format. So you write the function implicitly. Implicitly just means you can't separate the terms, so something like this. So you write the function implicitly, you just do this. You don't worry about changing your x or your y, it's literally what they give you, so t and v, then the function, and then an initial guess. If he's really nice, he'll tell you what the initial guess is. I'm just going to guess 1, 1 here. And looks like we have another problem. Turn a vector of fitted values the same length as a y. Okay. That usually means something like this. Yeah. So you should also get really good at debugging, and usually the biggest source of your errors are going to be these dots. So again, be more careful with the dots than I am, but I also haven't done this in a year, so I have an excuse. Okay. So I'm just going to keep throwing more and more examples of this curve fitting at you until you finally understand what's happening. So let's look at another recitation. So this one is pretty much the same jazz. You can do some flavor tests. We're going to have to use this file. I should already have it. And we're going to first do it with basis functions, and then we're going to do it with nlinfit. So let me just clear this first. And we'll get started. Okay, so I'm going to load the file he told me to get. And let me just check to make sure what this file actually is. Okay, so it's got 2 columns. No. Okay. So the first column, it looks like, is going to be the temperature from 0 to 50 in increments, and the second column is going to be this k. So again, he always gives these initial vectors as your values. So that's going to be, let me just name this. Okay, that's the first column. I guess we'll call this temperature. Hopefully we won't have to do any conversions. And the second column we'll call k. Alright, so cool. So again, basis functions. So you're given 2 options here. This one, which is written implicitly, so we can't use the basis functions, and this one, which almost is a polynomial but isn't because of this term. Remember, if you have a polynomial of degree 3, you have a 3rd degree term, a 2nd degree term, a 1st degree term, and a 0th degree term. You can't have negative exponents, so this would be impossible to do with a polyfit, which is why they don't ask us to do a polyfit. We're going to use basis functions instead. So again, you're going to have a column vector for every term you have depending on your dependent variable. So we have 1, 2, 3, 4 terms. So that's why our basis function, well, we're going to have 4 of them. So we're going to have a coefficient matrix that has 4 columns. So I'm going to make that now. So we have t minus 1, t, so I'll add some commas in here to spice things up, t squared, and t cubed. Okay, and that they're all column vectors, so that's cool. We didn't screw that up yet. Okay, and then again we need to look at what is on the other side of our equation as the independent variable. It is not going to be k, it is going to be 1 over k. Again, you look at exactly what is over here on the other side of the equation and you use that. So y is going to be 1 over k. And then to get the parameters, again, we just take this coefficient matrix and we do left division, and that's what we get. Okay, so the next question is, how do we do it with nlinfit? Well, again, the setup for nlinfit is identical every time. You take the function that he gives you written implicitly, make sure not to screw up any of the dot operations, which is the difficult part, times t plus 3 times t dot squared plus c4 times t dot cubed. Maybe I got that right the first time. Yeah, cool. For now, just nlinfit. Again, you don't need to worry about what's on the left hand side, what's on the right hand side. You literally just use what they gave you. So the dependent variable is t, the independent variable is k. We have our function, and we have an initial guess. Does it tell us what to use for the initial guess? Okay, it wants our guess to be what we found in the previous part. So I'm going to call this that, and we'll use that as an initial guess. Undefined variable. Okay, I'll just run that and that. Okay, so that's all you need for the linfit. Again, all you need to do is rewrite what he gives you as an implicit function of two variables, and then you need to just put the dependent variable, the independent variable, the function, and then a guess that he'll usually supply you with. Okay, let's do even more problems. Okay, so again, he gives you initial values for dependent variable and independent variable. So let's get those. I really hope you enjoy watching me put data points in, because I sure as hell love entering them. 3.3, 3.9, 4.2. I'm going to transpose that because we're probably going to need it to be transposed. 18.1, 0.21, 0.20, 0.20, 0.19, 0.18, 0.16, 0.16, and transposed. Okay. And I don't want to see those, so I'm going to suppress the output. So in this problem, he gives us the initial values, and he first wants us to use basis functions again, then he wants to use Polyfit, and then he wants to use nlinfit. Are you starting to recognize a pattern? Okay. So basis functions. What does he give us to work with? Well, he already gives us the equation we're modeling. Again, why do we have to use basis functions? Because we have a term down here that can't be expressed as a polynomial. So our coefficient matrix is going to be, and this time he didn't tell us the basis functions, so hopefully you could figure it out. It's going to be x to the negative 1 over here, and x over here. So we're just going to do exactly that to make our coefficient matrix. As for our y, it's what's exactly over here. It is not y, but 1 over y, because that's what's on the left-hand side of the equation. And that works fine. All you need to do is left divide that, and those are our coefficients. Okay, let's do it with Polyfit. Okay, so again, the syntax for polyfitting is you're going to take your dependent variable, compare it to what's on the other hand of the side, use that as your independent variable, and give the highest degree. So the highest degree over here is going to be 2. Notice that when we get the returned vector, we are going to get 3 terms, but the middle one we don't have to worry about because there is no term with a dependency on x to the first. So again, polyfitting, I guess it helps to look at it this way. X over y equals c1 x to the 0 plus 0 x to the 1 plus c2 x squared. So when we polyfit this, we are going to use a dependent variable of x. Our y is going to be this entire group over here. It might be weird to see x in the y term, but it's totally fine, and we're going to have that. So in the code, it's going to look pretty similar. xi over yi. I'm probably going to have to change that in a sec. And yeah, that's what I thought. And there you go. And again, this middle term here corresponds to the x to the first power. So that's not going to be used because there is a 0 in front of it. It does not appear in this expression. Okay, and lastly, the nlinfit, which corresponds to this, because again, it's an implicit function. We cannot write these terms explicitly. So, again, well, first we have to write the function depending on c and xi, and that's going to be 1 over c1 over xi plus c2 times xi. Hopefully I got that right. Nlinfit xi. Again, for the nlinfit, you don't have to worry about what is your actual x, what is your actual y. It's just the dependent variable, the independent variable, the function, and then the guess. Do they give us a guess? No. Well, I guess I'll just choose 1 and 1.4. Just arbitrarily. And cool, we found them. Alright, so the last problem I want to do is the one that I believe you guys did for a recitation this week. Don't tell anyone. Damn it, spelling clear. Okay, so same stuff, different day. Okay, so again, you were given two vectors. A vector of the independent variable and a vector of the dependent variable. So I'm going to type in those values. 250, 260, 270, 280. There's probably a pattern I could use for this, but whatever. Just type that in. Up to 350. Alright, cool. They're already in Kelvin. I don't have to worry about converting them, and I'm going to put this as a column vector. The pressures 260, 504, 1184, 29110, 3913, 9462, 841, 16, 952. These are pretty big numbers. Move this over momentarily. 41529 86 3 77 537. Again, transpose, and hopefully everything works. I know it's a lot of numbers, so things could go wrong. Okay, so part A wants us to do an nlinfit. Okay, usually they don't start with the nlinfit, but that's totally fine because nlinfitting should be pretty easy at this point, especially when they give us the guess values. Okay, so again, nlinfit, you don't need to worry about finding a particular x or y. You just use the dependent variable, then the independent variable, then the function, and then the guess, which in this case is 1000, -1. Okay, and of course we need to write the function, which is always going to be c, and the dependent variable. And it's written very nicely up here. Okay. So C1 minus C2 over C3 plus TI. Probably dot goes there. Got some errors, cool. Okay, yeah, that shouldn't be there. And what else we got? That should be bracket, and what else we got? That should be parentheses. Okay. And those match the values that are here. Okay, so in this case you actually did need to make one small adjustment in taking the log base 10 of a p. But that's pretty rare. Usually because when they give you this, they literally have the other side of the equation written in terms of the independent variable, because that's almost the entire point of doing the nonlinear regression. So I guess check to make sure y is in fact y, or the independent variable is in fact the independent variable, but this is pretty rare and you should be able to easily recognize the mistake like I did. I was like, alright, 10 to the 15th is clearly not these numbers, so it's a pretty small adjustment. The other thing it wanted to do is use Polyfit. Okay, so the interesting part here, and why it might have been a little bit of a mean move on Sophocles' part to give you guys this as your first curve fitting exercise, is that this equation is not written in linear form. It is written implicitly. The other thing he tells us is that we can use the coefficient a. So we could treat a as a known. So that helps us write this in linear form. So you actually need to do a little bit of math to transform this into a linear function. So let's do that here. 10p is a minus b over c plus t. Okay, so I'm going to move the a to the other side and multiply by -1. That's going to give us this. Okay, then the reciprocal. So just take this. And over here, we're going to get t plus c over b. Okay, and what can we eventually transform this into? We can transform it into b over a minus log base 10 p minus c equals t. Okay, so what's cool about this problem? Well, as previously, your dependent variable is actually going to be your independent variable in this case. So remember, this entire expression down here in the denominator is known. So we have values of pressure and we have A. So then what is really going on over here? Well, how is the easiest way for me to explain this? Maybe it's better to do a polyfit in terms of something else that's easier to understand. We could try that. Well, actually, no, I guess I'll just go with this. Okay, so the polyfit we're doing here is going to be of first degree, and the coefficients we're going to be solving for are going to be b and c. So I'm probably going to try this a different way, but I at least want to show you guys the way that works, or a way that works. So again, our dependent variable here is going to be this guy in the basement, a minus log 10 p. Get the right number of parentheses, hopefully. Then we're gonna have t on the other side, and it's gonna be first degree. I need to find a because we assume we know a at this point. And okay, it should be pi and ti. Okay, so this gives you a pretty good approximation of b and c, but the c isn't negative. So what's a possible cause of that? Well, we just polyfitted something that is not a polynomial, which is problematic. So I'm going to try to do this with an actual polynomial. So how do we do that? We take this term, we make it t times 1 over b plus c over b. So that reverses it so that our dependent variable is in fact a dependent variable. So this has degree 1 and this has degree 0. Okay, so let's try that. So we could use ti. I shouldn't have deleted that. We're gonna need it. Ti is fine here, and that should be fine there. But pay close attention to what we're getting as our returns. So are these B and C? Well, no, they aren't. The first one is 1 over B. So if we want B, we need to divide that. And there, now we have B. The second term is C over B. So we need to take that first term, and if we want C, to multiply by that. And now we have what we want. So what did you learn? Don't try to polyfit things that aren't polynomials. Make sure you have them in linear form, and things will work out nicely. So we had a few mishaps, but I think overall you should be able to do well in the exams by basically applying these ideas. So I'll leave you guys with that.